Okay, so last lecture I ended with a statement of a theorem. I write it here again. Theorem. It says that submodule of a free module is free, and we are actually over Z. We are talking about it. So suppose the W is a free abelian group of rank M, and let U be a subgroup of W. Then U is a free abelian group and its rank is less than or equal to M, namely the rank of the whole group. Okay. Proof. So statement anyway we understood last time. So only proof, I have to give some idea how to prove this. Suppose C is a basis. So we have already agreed that we are going to write ordered basis within or round bracket, just to separate it from any other basis. And here we are always taking ordered basis. For this is a basis for W, the whole space, namely the free abelian group. And let U, sorry, already I have assumed this, and set a set of generators denoted by say B, U1, U2, UN for U. So now here the question can be, how do I know that U is finitely generated? So here remark, which actually we are going to prove after proving the statement, without assuming of course this theorem, that submodule, subgroup maybe, subgroup of a free abelian group is of finite rank. Of finite rank is finitely generated. So this statement we shall prove a little later. So it's not that we are not going to prove it. This statement will be proved, but after some time. Okay, we are assuming now that U is, this is an additional hypothesis, that the subgroup we are looking into are finitely generated. And later we will know that all subgroups of a finitely generated abelian group, a free abelian group, is finitely generated. Okay. Suppose the jth basis generator, the jth generator of the subgroup U is written as Aij Wi 1 to M. So rank is M, so I have a basis which has M elements, and any element Uj I am writing as a combination. In fact, this Uj for j equal to 1 to N is a set of generators of the subgroup. Okay, so an indicate notation again we are using A to be Aij, whose columns are the coordinate vectors of generators of U. The generators we have picked for you. So what we have, that from Zm to W, we have a isomorphism which is defined by the basis. right? See, we have seen such a thing that x going to bx. Here I'm writing c. So x going to cx is an isomorphism of groups. Similarly, I have here a map from Zn to U, and this one is given by B, the set of generators. And this map, since U1, U2, Un generates U, this map is onto, need not be an isomorphism. And U is a sub of W, so I can always consider the inclusion map, right? And how I see A is this map. When I apply on a column of size n, I get a column of size m by post multiplying the vector. And this is how we understood it that time. So in the diagram, the right vertical arrow is an isomorphism. I is the inclusion map. Now what I am going to do, diagonalize A, right? Any matrix defined over integers can be diagonalized with certain good properties, namely diagonal entries d1, d2, dk, and after that all zeros. Di divides di plus 1. This is the property you had. So that we saw last time. So that's what we do. And when we do it, so that the diagonal matrix A prime is related to A by post multiplying by an invertible matrix and pre-multiplying by another invertible matrix, and which are related to the change of basis. So in fact, how they are related? Where this new basis B prime of so I should say maybe generators, new basis of Zn, which is B times Q. And C prime is C times B. So Q is an invertible matrix, but what we had B is not a basis of U. So again, generators just got changed. But I can come back to B because Q is invertible. So I should not say here it is a new basis, it's a new set of generators, right? B prime is a new set of generators. So I just correct this. Of U. And I know that P and Q are invertible. Their sizes may be different. C, P, yeah, P is GLM Z, Q is GLN Z, right? Okay. So again, you can, maybe I can draw the diagram. Zn to Zm, I had A, then I am applying some Q invertible map from Zn to Zn, and then Zm to Zn respectively. And new matrix is A prime, which is from Zn to Zm. And maybe here, this is U, and W is here. Here. And this is the inclusion map, which is whether I look at from the top or bottom, they're same. I. Okay, I hope this diagram is fine. So red one is above and blue ones are behind. Okay, so So when we do this, what happens to A? So A prime becomes some D1, D2, dk, and then zeros. There may be 0 columns, there may be 0 rows, and di divides di plus 1, where I is less than k minus 1 and 1. Okay. The number k of non-zero diagonal entries of A prime is bounded by minimum of the two. It cannot be more than m and n. And the range under the map, so maybe I should give a name here. This is here it was B and this was C. This has now become B prime, and now here it is C prime. So now with respect to map C prime in the diagram is a linear combination of what? Giving new name, uj equal to dj times ej, where j is between 1 to k. And other uj, there may be more j, k may be smaller than m and k. So in that case, I'll have non-zero. Zero, some of them will be 0 for k less than j less than equal to n. Okay. Because I had originally u1, u2, un, so I would like to have another new ones, but some of them will become 0, so I have to ignore them all. So remark here is that if u is the 0 subgroup, then empty set will work as the basis. Is the basis of u. This convention we had in linear algebra over fields, and over rings also same convention, that zero abelian group is a free abelian group and generated by the empty set. Okay. Suppose this A, which is m by n with integer coefficient, is diagonal and n is less than or equal to m. Once it is diagonal, I can assume that n is less than or equal to m. Is that fine? There can be 0 columns. 0 rows can be ignored. Okay. Then this uj equal to dj times wj is a basis. Why? Because what we can see that if I have a combination of these, say I supply coefficient aj to uj and add them 1 into k, maybe n now because k has become n, because I am now considering the situation that n equal to k. Okay. So this is equal to 0 implies summation aj. What is uj? It is dj wj, and this is equal to 0. So aj dj times wj is equal to 0. So but I know that w1 w2 wn is a basis, so I'll have Okay, so there is a problem. So therefore, AJ DJ has to be 0, and this implies you see here this guy n is less than equal to m, so there is no problem here. You see, I have w1, w2, wm up to m, so I'm utilizing only n of them here, and there w1, w2, wm is a basis. Therefore, such a linear combination is equal to 0, possible only when coefficients are 0. So this is 0 for every j, and therefore aj has to be 0. Okay, so therefore linear independence condition is verified. So next, I have already said that U is finitely generated. We are going to see it after some time. So before that, maybe we just consider an example. Let M be the free abelian group generated by E1 and E2. That means 1, 0 and 0, 1. Right? The grid, if I can draw these points, maybe say this is 0. So suppose this is 0, then this is 1, 0, this guy is 0, 1, then others are combinations. So it is then not easy to see which one is the origin. 0, 0. So this is 0, 0, and maybe I am looking at these E1 and E2. Then anything else is a combination. So of course this is infinitely extended. Okay, so this is denoted by say C, and let L be the subgroup generated by B, which is V1, V2, where this V1 is 2, 1, and V2 is minus 1, 2. So if I have to see here in the same diagram, if I have to locate 2, 1, 2, 1, so it will be here 2, 1. Is it visible?
Yes, it is.
Okay, so then minus 1, 2. So I will come back backside, and then go up. These guys. Okay. So I have somehow here this. So they will generate a subgroup of M, Z linear combination I am going to write, that is L, and it is a subgroup of M. So that is not a problem. That B is in fact a basis. That B is linearly independent is not a problem. Okay, so now what diagonalization of A, namely the matrix A that defines the subgroup, namely 2, 1. First column is the first basis vector, first generator. The second column is the other generator. Then I don't remember whether we saw this diagonalization, but in this case A prime turns out to be 1, 0, 0, 5. And in this case, Q is 1031. So let us verify also whether this is correct. So that A prime is Q inverse AP, which is 1005. So what is 10? Maybe I just multiply them. So A prime is 10 minus 31, that is Q inverse. Then AP, I am going to directly multiply AP. AP, the first member is 1, second one is 1, 5, then 10. Then 1, 1, 1. So there is a mistake, I think. Minus 3, 5. No, this is not correct. Sorry.
This matrix 1, 1, 5, 10 is wrong. I think 1, 0.
Which one is wrong?
AP, P into A into P product.
Right. So I'll see that. I perhaps multiplied with a wrong matrix. Yeah. So I have to multiply A with P, not A prime with P. So 2 minus 1, 1. 2 minus 1, 0. Sorry, thank you. And 1, 2, 3. Then 1, 2, 4, 5. Then I get 1. Then I get 0, 3, 0, then 5. I think this is, now it is 5. All right, so then what is B prime, the new basis? B prime, I know that B prime is by definition, the change of basis matrix is BP. So I have to multiply 2 minus 1, 1, 2 with P, this one. So again, we know, right? I'm assuming that we know how to find P, that we have seen with example. Apply elementary row and column operations on A, then correctly write down what is P and Q inverse rather. Okay, so this is 1035, and which I'll think like 13 transpose and 05 transpose, and C prime in the domain space is 1001, the basis of M E1 E2, right? This matrix I'll multiply by Q 10. What is the change? This is just identity map, so no problem. I'll get just 1301, and which I write as 13 transpose 01 transpose. So now let us again see with respect to this basis. Yeah, 13. So maybe here, this is 13. Maybe this is not an enough space. Maybe I'll go to the next page. So this is C prime, this is B prime. One, 3, somewhere here. Then 01, somewhere here. And C prime is same thing as 13 and 05 here. So this is just multiple, other one is fine. these two vectors, and subgroup has got these two, the yellow ones. So that's a subgroup. Okay, so these examples are helpful to us. So we'll go to the next idea that we need of generators and relator or relations. Okay, suppose A is an M by N matrix with entries from R, a commutative ring with unity. Then I have a map from Rn to Rm. I know how to send, where to send this n column. I'll simply post multiply it by the matrix A to get a column of size M with entries from R. So definition is the module Rm upon ARn. Okay, Rm, the right hand side, the codomain space or codomain module quotiented by the image module. So since module is is always abelian, so there is no condition. Then when you can take quotient, I have taken simply the quotient module. So the module this is said to be presented. Sorry, this is looking bad. Presented by the matrix A. So when I have a matrix of size M by N, then I'll simply look into Rm and go modulo the subspace, which I get by post multiplying every element of Rn by A. So more generally, at least it looks more general. If an R module V is isomorphic to this quotient Rm upon ARn, then we say that A is a presentation of the module R module V. Just quick example, an easy example. First, to start with, from Z to Z, I look into this map, simply multiplying it by some n. Okay. So then what is the module I have in my mind? Students can help me. What is the module I have in my mind? What is the module I am talking about here? Just compare. Any comment? Am I connected or they got disconnected?
Yes, we can hear you, sir. Yeah.
Yeah, okay. So we have in mind Z upon A is this multiplication by N. So N.
Yeah.
So we have this in mind. Then what is the presentation? So I'll simply say the presentation of this is this matrix and
Yeah.
1 by 1 matrix. That's all. So this is the simplest example we can have in mind. Okay. Proposition. If Rm upon a matrix times Rn, when I am writing a matrix A times Rn, it is understood that A is a has got how many rows? n columns. See here, m rows, n columns. If this is isomorphic to V, R module V, this isomorphism is isomorphism of R modules. Then V is generated by what? Again, students can help me. Generated by which elements? You see, come back here. Can you tell a set of generators for the image of this? I'll multiply A to the basis of Rn. For example, standard basis. Is it okay? A E1, A E2, like this?
All columns of it.
Okay. So you are suggesting that if I have A, B, C, D, then if I multiply to 1, 0, then what am I going to get? A, 0, A, and then C. That's right. This is the column. Then A, B, C, D, I'll multiply to 0, 1, I'll get the next column. So we can generalize this too. So this V is generated by V1, V2, Vm, where Vi is AEI, the ith column of A. Yeah. So
So
this is
the columns are n, right?
columns are
There are n columns.
n columns. So what have I written? I have written M. So I should write, yes. This is what you are saying, N. Thank you. Yeah. Next, this is say A. B, if Y equal to say Y1, Y2, Ym. Transpose is an a column of size M with entries from R. Then By, which is combination of this, maybe I call it B. Vi, Yi. Should write N here. So what is that M about M and N? Any confusion here? I have E1, E2, En, that is fine. So therefore I have got E, V1, V2, Vn. Oh, I see. I'm sorry, to start with, I have written N here. I should have written M. Then there is no problem. No, this is fine. I'm looking into Rm upon ARn. This is fine. All right. This is equal to 0 in V. And this is true if and only if what? Y is a linear combination of what? Columns of A. By is 0. That means it is a linear combination of V1, V2, Vn. This is my B. Y is A of X for some X coming from Mn. Okay, I think this does not require a proof. This is just an observation. So just another definition, an element Y, which is in Rm. Again, we should see that this is Rm is nothing but m by 1 in R, okay, is called a relation vector, or relation, maybe just relation, for the module V generated by B if By is 0. Okay, so B is a set of generators, and an element in Rm is a relation if such a combination is 0. Okay, so what I have, Rm to V, B is a set of generators, so I know how to multiply. V is generated by m elements, so kernel will be generated by some n elements. Okay, so I am not writing any matrix here. We are just saying that when there is a Y in Rm, which when I apply B, I should get 0, and that is a relation. Next, a set S of relations. Set of relations is a complete set of relations if every relation is a linear combination of relations in S with coefficients from R. So maybe now when we are writing this, maybe we have, the idea is that can we have a finite set S such that every relation is a linear combination of relations in S. Okay, so what is the meaning of this? Therefore, what is the set of relations? All relations are given by ARN, right? ARN. So whether we get S, when I look at the submodule generated by S, can I get whole of ARN inside Rm as an R module? So an example, Z module V is generated by, say, V1, V2, V3 with relations. So this is not a basis. Okay, this is just a set of generators. So this V1, V2, V3 are elements coming from maybe R3 or R4 that we are going to see with relations 3V1 plus 2V2 plus V3 equal to 0. 8V1 plus 4V2, 2V3 equal to 0. 7V1, 6V2, 2V3 equal to 0. 9V1, 6V2 plus V3 equal to 0. So some 4 linear combinations are 0. So set S. Therefore, what is S? So we are writing Y is a linear combination of V1, V2. So, and so we have to talk about some metrics now, right? So what is the matrix I have in mind now? What I'll do, these coefficients I'll take as the first row: 3, 8, 7, 9, 2, 4, 6, 6, 1, 2, 2, 1. Okay, so we have a Z module generated by some 3 elements. Okay, so where am I looking V inside?
R3, no, Z3.
So I know I have a map from Z3 to V. Is it correct? Z3 to V, I have a map. If you give me X, Y, Z, I'll say that XB1 plus YB2 plus ZB3 is an element in V. If you tell me what are V1, V2, V3, then I'll simply write that take those linear combinations. Right?
So this shouldn't this A be, instead of 3/4, shouldn't it be 4/3?
So what
Because
do you
if
want
we
A to be?
like if we multiply these V1, V2, V3 with A, we should get these zeros.
So do you want to get something like this, Z4 to Z3, some matrix A? This is what you mean?
Yes, sir.
So if I want a matrix like this, and that I'll think then finally that Z3 upon A Z4 is my group V. This is what is a plan, right? So if your map is from Z4 to Z3, what is the number of rows of A?
Then it's 3.
3. So that is the idea.
But if we simply like what we did in linear algebra, that
Same thing we are doing. See,
but then the
Z4 is,
matrix will be transposed, right? Of what you have written.
okay, so you see, Z4 is not the kernel. A Z4 is the kernel of whatever map you have here.
Okay. Okay. Yes, sir.
Okay, so just we have to remember that columns of the presentation matrix, and normally we don't do presentation matrix in linear algebra, are coefficients of the relations. So relations are linear relations. So how to find presentation matrix? If V is given, maybe V is given by this, generated by B, which is V1, V2, Vm. Then what we have? We have a map, which I call Phi, maybe. Now I'm writing psi, from Rm to V. Right? This is what we have said, from R3 to V. Same thing I'm writing more generally. What is the map? Any x going to Bx. And this is a surjective map. This is fine. Now the kernel. Kernel of psi is an R module of Rm, and what? Rm upon the kernel is isomorphic to V. This we know by definition of V, because V is generated and I have a surjection from Rm to V, and kernel, if I go modulo kernel, then I get the range isomorphic to V. Okay. So here kernel psi is the module of relations. Is it fine? This is the module of relations. Maybe you call it W. Suppose W is generated by, the kernel is generated by, say, C, which is the, say, W1, W2, Wn. Then we have a map from Rn to W. Is it fine? See, from Z4 to Z3, actually Z4 to W, right? This one is, although Z4 to Z3, it is Z4 to W actually. So, which is contained inside Rn, defined by this C. So if you tell what is the set of generators of W, then I know a map from Rn, where n is the number of generators in W, okay, to Rm or to W. If Aj is the column vector Wj in Rm, then A1, then A2, like this. An is the presentation matrix. This is what I mean. This is the image of Ej, which we are calling Wj. Okay. So that is what the starting point was. Image of Wj is Ej is Wj. So W is equal to Arn, the kernel is the kernel of the map Rm to V, which we call psi. Then V is the given module is Rm upon V, sorry, W, which is same thing as Rm upon Arm, because we are now writing W as Arn. This map is surjective, eta is surjective. So this is how to find. So we have to, what are the two things we need to do? Given a abelian group V, we need to know a finite set of generators. Then given the number m of generators, we have a map from Rm to V. Then we have to look into the kernel. Then we have to find a finite set of generators of the kernel, right? And that when I know this set of generators, then there is a number n, the number of generators from Rn to W, the kernel. We have a map whose matrix I have to write now, namely Wj gives me the matrix. The jth column of the matrix are given by the components of Wj. Okay. So again, the same remark. that if the set of generators of V, if the set of generators of V is a basis of V. The set of generators is actually a basis of V. Then what is the matrix? What is the matrix? So what we started with, a set of generators. It may be a basis, right? If it is a basis, what do I know about this map psi? Anybody?
Surjective.
When it is a basis, it is in fact an isomorphism.
Yeah.
So the kernel is 0.
Yes.
In that case, what is C? Do I need any C?
It's empty.
It is empty. So in that case, A is empty. A is empty. So there is no matrix that way. Okay, so some remarks or proposition in the proposition. Let A be an M by N presentation matrix for a module. Then the following matrices A prime present the same module. So if you have slightly different module, how slightly, that is what is we're going to say, then they may have the same module. They may present the same module. For example, if A prime is obtained from A by simply post multiplying by an invertible matrix, then they have the same module structure. Is it fine? Because I can go from one set of generators to another set of generators because Q is invertible. Is it fine?
Yes.
Similarly, can I say that I can post multiply also?
Yeah.
A prime equal to A times P, where P is an invertible matrix. That writing Q inverse in the previous one, that we know that there is a reason why we just write Q inverse. Even if you write Q, it is fine. They are invertible matrices. Okay. Third, A prime is obtained from A by deleting 0 column. Is it fine? You can delete a 0 column. 0 column, and so there is no relation there. No problem. We'll go back to this first state here. So every column is a relation, right? These are 4 relations. So if I have a 0 column, that means I am multiplying 0 times V1 plus 0 times V2 plus 0 times V3 equal to 0. That is anyway true, identically true. So that does not give me a condition if I have a 0 column. So therefore I can drop a 0 column. If the jth column of A is EJ, that means jth column is having 1 in the position, say, okay, not EJ, maybe it is EI. Okay. And A prime is obtained from A by deleting the ith row and jth column. So how, let us see, what does it mean? So I have certain columns. So some column, say this is my jth column, and this has got some A, B, then 1, C, like this, something are there. Okay. So what I am going to do, I'll put zeros here. 0, 0, 1, this one, 0. Jth column has
Sir, jth column is EI.
jth column is EI. Right. I'm sorry. So I'll just correct this one. Jth column is EI. That's right. 0, 0, some 1 here, then 0, 0. That's right. So this is my ith row. So I can have anything here. So these entries may not be 0. Right? There may be something here. So what we can do, we can drop entire jth column and ith row. So the idea here is that you can apply elementary row operation and make these, what I have, wherever I put a cross, equal to 0, because this is 1. If I have, say, A here in the, so suppose this is A, then what I can do, I can multiply jth column by A and subtract from the next. And then that particular coefficient will become 0. So I can make them actually into 0. So therefore we don't care whether they are 0 or not.
Also, I think it represents the jth column. If it is EI, it is representing the relation which says V
Yes.
I is 0. So
Yes,
in
that's
other
right.
relations, we can replace VI by 0.
That's right.
Okay.
That's right. Vi equal to 0. Yeah. So these relations, when we remember, then it is very handy, because when you have a presentation matrix, then you can convert into simpler form by following these rules. 5, adding a 0 column. And we know that there is 0 relation you have added. There is nothing new. And the last one, including some row, I mean such a row, basically, some row with I and a column. Some row with 1 in the ith component and how to write this, including some row. I want to include a row and a column, maybe, and a column in the ith position. And so row should have 1 in the ith column. The ith component of the row should be 1. Yeah. Such that the ith component of the row, new row, is 1. Then there is no problem.
Is it like the reverse of 4th?
Yes,
point?
yes, exactly. So reverse of 4th is 6. Reverse of 3 is 5. And I mean, if we are convinced with 3 and 4, then 5 and 6 are also fine. Because such a thing is a symmetric thing. Okay. So let's see an example with that relation matrix. 3, 8, 7, 9. Oh, time is affecting. Okay, after this, I'll stop. 1, 2, 2, 1. So I apply, maybe quickly I do this. So I'll make the 3 and 2 into 0 by multiplying, applying suitable relation row operations. R1 to be replaced by R1 minus 3 times R3, R2 replaced by R2 minus 2 times R3. Then I'll have 2, 0, 2, 1, 2, 2, 6, 4, 1. Then I apply column operations. So C2, the second column, I replace by C2 minus 2C1. C3 by C3 minus 2C2. And C4 replaced by C4 minus C1. Maybe this is C1, just verify. So I'll have 0, 1, 0, 0, 1. Then I'm making this one 0 because subtracting 2 times C1, 0, 2. So these are not going to change. And I'm converting this into 0. So this is C1. Yeah. Then what I can do, I can drop this. And I could do it without doing this also, right? Yeah, without doing this also, I could simply drop. Yeah, because of the rule. I do not even have to come here. I can directly come from here. What is that? What is that? 2, 1, 6, 0, 2, 4. Yeah, I don't even need this. I can come directly. Then R2 replaced by R2 minus 2R1, 2 minus 4, 1, 0, 6 minus 8. Then you see this one again, I'll put in this way. So I'll have minus 4 minus 8. And then I'll multiply by minus 1 and then do a column operation to get 4 and 0. What is that? Multiplication by minus 1 and C2 replaced by 2 C2, right? And then this will give me simply 4 because 0 column I can drop. So the module represented by A is, can you answer this? What is the module A represents?
4.
Z upon 4Z.
Yeah.
N represents Z upon NZ. Okay, so last example for now, then I'll close. Say 5, 0, 0 represents. What is the answer? If I have only 5, Z upon 5Z, that I agree. Then I'll have 5 upon Z5. Sorry. Z upon 5Z. But I have 0, 0. What is the meaning of that?
Zero rows can be deleted.
No, we cannot delete. 0 columns can be deleted.
There is no point for deleting rows. Okay.
Yeah. So what does it mean? 5v1. Go back to this one. What does that mean? 5v1 is 0, 0v2 is 0, 0v3 is 0. 0v3 is 0, right?
The kernels.
5v1 is 0. So therefore v1 is coming from here. But 0 times v2 is 0. But this is always true. There is no condition on v2. 0v3 is 0. There is no condition on v3. That means they are free. Is it fine? 2 copies of Z.
Yes.
See, generators are v1, v2, v3. 3 generators are there. First generator, there is a condition. Other 2 are free. Is it okay? Is it okay? So when I have only 0, what does that mean? 0, 0, 0.
All are free.
Yeah, if I have only 0, that means it is Z. If I have column of 0, 0, 0, 3, that means I have Z3.
Z3.
Yeah. So you see, go through this one once and get used to. Okay. So this is new, that going to the kernel and finding A. Okay. So I'll stop here. Thank you.